Good afternoon, friends. Hope you all doing very well. So this is just 1 week left for the coming exams, and hope you all are doing good practice and revision. So today we are coming with the rapid revision series, one shot number 13, and the chapter is dual nature of matter and radiation. That is we can call that we started the modern physics chapter. So we can expect total modern physics chapter. We can expect 5 to 6 questions, and definitely this is the must-do chapter for everyone because this chapters, that is dual nature of matter and radiation, which we have done in physics, in chemistry as well as in physics. Again, the atoms chapter is also there in chemistry also. So this will be like scoring chapter over there, obviously. And let's begin this today's journey. So what is the topic that we have? In the first case, we have the particle nature of the light, we have the photoelectric effect, then we have wave nature of the matter and radiation, that light behaves both way as a particle. For that, we will discussing particular topic, that is a de Broglie wavelength. So first one is that if we talk about this particle nature of the light, so particle nature of the light, that all the lights whatever we get, that is nothing but it is made of small particles, and the smallest particle of the light we have, we call it as photon. So all electromagnetic radiation, we have gamma rays, we have X rays, we have UV rays, we have visible rays, we have microwave. Whatever the electromagnetic radiation we have, that is made up of a small number of particles, packets of the energy. That small packet is what we define photon. And what is photon? Has definite energy and momentum. And what is a photon? Always travel with the speed of the light. What is speed of light? 3 equals 10, 3, that is 3 into 10 to the power 8 meter per second. And if you talk about the energy of the photon, that is given by hc by lambda, where h is the Planck constant, c is the speed of light, and lambda is the wavelength of the light, is also equal to h into mu, where mu is this again frequency of the light. And if we solve this particular term, that is h multi, what is h value of Planck constant? 6.626 into 10 to the power minus 34 joule second. If you write in terms of the electronic volt, we know that relation, what is that? 1 electronic volt is how much? 1.6 into 10 to the power minus 19 joule. This is the 1 electronic volt we have. And if we talk about this h value, 6.6 minus 34 joule per second. If you write in terms of this h into c, that is the Planck constant multiplied by speed of light, that h c together value we have, that value is how much? 4.14. This particular value, that is 4.14 10 to the power minus 15. This is the value of the h. And if you write this together, hc value, we are getting this particular equation, that is 12440 divided by lambda. When to use this particular expression we have? When h and c in electronic volt we are writing, and lambda is in which? Angstrom. Lambda is in angstrom. Then we'll be using this particular equation over here. So again, the energy can be quantized in the form of the photon, and energy of the each photon is given by hc by lambda, where lambda is the wavelength of the photon and mu is the frequency of the photon we have. Next, if we talk about this momentum of the photon, so what is the energy of the photon we have? Energy of the photon is given by hc divided by lambda. And we know in this chapter only we'll be discussing what is that lambda. What is lambda? The lambda is h by mv, h by p. So lambda is h by p. This is what we define de Broglie wavelength, that is having de Broglie wavelength of the particle, that is having momentum p and wavelength is lambda. So from here we can calculate. So I want to find momentum of this. What is momentum? H by lambda over here. Putting this value over here, h by lambda is p. Energy of the photon, I'll be writing this. The photon energy is given by h by lambda. What is h by lambda? P multiplied by c. So this will be p multiplied by c. And from here we can write momentum of the photon is energy of the photon divided by speed of the light, it also equals to h by lambda. So this is the expression we are getting it from the momentum of the photon we have. Next, if we talk about the intensity of the light, okay, let's talk about the intensity of light. Before we discuss that, so first one is that given one photon is having energy of hc by lambda, two photons will be having 2 hc by lambda, three photons will be having 3 hc by lambda. Like that we will be having how many photons? N photons will be there. This all will be having n hc divided by lambda. This is what energy of the light. One thing that we should keep in mind, the energy of the light. Energy of the light is n photons. Energy of one photon multiplied by n. How many times? One photon hc by lambda, two photons 2 hc by lambda, three photons 3 hc by lambda, n photons will be there. That is n hc by lambda. That is energy of the light, because light consists of n photons, not single one photon. One photon energy is only hc by lambda. So energy of the light is n hc by lambda. Here we define intensity. What is intensity in general? Intensity is what we define is that it is the energy falling on a given area per unit time. So energy divided by area divided by time. So energy divided by area divided by time. Okay. So suppose, let's say this is any surface over here, and light energy, that is photons, are falling at the rate n by t. So photons are falling. So what is the total area? We take it as A, and total energy we can calculate from here. How many photons are falling? N photons are falling. In how much time it is falling? T time. N photon by T. So intensity we can write here energy by time. What is energy by time? Power. There is one more formula, that is we have the power divided by area. And second, if I write energy, what is energy? Whose energy? Light energy. That is NHC divided by lambda multiplied by area multiplied by T. So from here we are getting this particular expression, energy equals to power divided by area, or I can also write here NHC divided by lambda into A into T. This is what intensity of light we have. We can check the intensity is directly proportional to number of photons. I is directly proportional to number of photons. I is inversely proportional to area of the surface. Okay. So if we have the bulb as a point source at this particular point, we will be focusing on this area over here. As we are moving over this area will keep on increasing. So for the bulb, that is, if you talk about this area, distance is r. So in intensity at this particular point will be given by power divided by area. This area, that is area 4 pi r square. If this one is 2r. So what is intensity at this particular point? We will be writing this intensity is equals to power divided by, it is spread in this larger sphere. That larger sphere is having surface area how much? 4 pi into 2r ka whole square. So this will be power divided by 4 pi r square multiplied by 4 times. So intensity is inversely proportional to 1 by r square. We have this discussion in the classes when we discuss for the point source. This is because of the point source. As we are moving away from this source, how the intensity varies. So near the bulb intensity will be more. As we are moving away from the bulb, intensity will keep on reducing. And how it will reduce like this? Because as we are moving, move away from the bulb, intensity of the light will keep on decreasing. That is 1 by r square. This is for point source. I is inversely proportional to r. This is for linear source of the light. This is for linear source. And last one, that is I is directly proportional or inversely proportional to r to the power 0. This is for planar source. So this thing that we should keep in mind using the problem solving from the intensity of the light, where r is a distance from the source. Okay. And what is intensity? N hc divided by lambda a. So from here, if they're asking number of photons per unit time, so n by t equals to I lambda a divided by hc. This particular call we call it as photon count. Okay, photon count. What is photon count? Photons striking the given surface per unit time. That is photon per second. So moving to next part of the chapter, that is a photoelectric effect. So what is photoelectric effect? It is the phenomena of emission of the electrons when the light of suitable frequency falls on certain photosensitive material. So for example, we have the alkali metals, that is sodium, potassium, calcium, cesium, francium. These alkali metals are very much photosensitive. What actually happens is that whenever any photons is striking that surface, what happens? Electrons will come out from their surface, metal surface, and it will conduct electricity. This phenomena is what we define photoelectric effect, that electricity is because of the light falling on its surface. So here we have in this particular setup, let's discuss what we have. Little bit theory will be discussing on this. So what we have here, this is one cathode. This is what we define cathode, and cathode is also we call it as emitter. So cathode is emitter in which electrons will be emitted. Okay, and the light of suitable frequency falls on the cathode. This cathode will be made up of some alkali metals. Alkali metals, and what is alkali metals? We already know from the chemistry, right? So these alkali metals are the most electropositive metals where removing electron tendency is more, means we can remove electron from these metals easily. So we'll call it electropositive elements, and from this we can remove the electron easily. So this particular cathode is of, we call it as emitter, that is made up of certain alkali metal materials. And what actually happens, this side it is connected to negative of the battery, and this side we are connected to positive of the battery, and this side here we have, we call it as, this one is anode. And what is anode? Anode is, we have given the name, that is collector, which is collecting the electron. Okay, this one is, we have given the name, that is collector. So what actually happens, the process I will tell you, when the light of suitable frequency falls on this particular surface, okay, electrons will eject out from its element, that is from its surface, metal surface. As once the electron will eject from the metal surface, the electron will move. It again depends on the frequency of the light. If the frequency of the light is small, then electron will move. If the frequency of the light just matches with the threshold frequency, then the electrons will not move. So here there is one particular term we define, that is threshold frequency. What is threshold frequency? So threshold frequency is defined as minimum frequency for a given material so that electrons will come out of its surface. So for example, if you are taking the sodium, so minimum frequency for a given sodium will be one particular value. So threshold frequency will be defined as the minimum frequency so that electrons should come out of its surface, minimum frequency of the light that we should give. So that is, we define threshold frequency. Then also we have term, that is threshold wavelength. So threshold wavelength, what is threshold wavelength? It is the maximum wavelength of the light which should be incident on the photosensitive material like this alkali metals, so that electrons will come on this. So if frequency is more than threshold frequency, yes, photoelectric effect is possible. If the frequency is less than threshold frequency, photoelectric effect is not possible. It is the reverse case of this threshold wavelength. If, because this one is maximum, if lambda is greater than lambda naught, threshold, that is photoelectric effect is not possible. If lambda is less than lambda naught, then photoelectric effect is possible. So these are the points we have. Then here we define one more term, that is the work function. What is work function? The minimum energy required for a given metal so that electrons should come out of its surface. We call it as work function, and that is given by, numerically it is given by h into mu naught. What is mu naught? Threshold frequency. And what is this one? So this phi naught we can write here, hc by lambda naught. And we have that relation between threshold frequency and wavelength. What is that? Mu naught is equals to c by lambda naught. Clear? So this is actually happening, work function. If energy of the incident photon is more than the energy of the work function, then electron will come out. Or energy is actually matches with this work function, then also electron will come out, but it will not move. If the energy is more than this, then electron will move. And let's see how we are relating this particular term with the mathematically, that is Einstein photoelectric equations we'll be using. In that Einstein photoelectric equation, what is that? Whatever the energy of the light that were incident, that is given by work function plus maximum kinetic energy of the electrons. So work function, whatever this energy, for example, if I take the number, let's say 4.2 electronic volt energy I am giving, energy of the photon, okay, and work function is given like, I will be solving here only. So this side, energy of the photon, that is energy of the light. So this is, let's say 4.2 electronic volt, and work function is, let's say 2.2. For example, I'm telling, I'm not giving any data over here. For example, 4.2 electronic volt, what is remaining? So for 1 electron we are having 4.2 electronic volt, that is energy of the photon, 2.2 electron volt plus maximum kinetic energy Kmax. So from here we can calculate what is Kmax. The Kmax we are getting here 2 electronic volt, that is a 2 electronic volt will be the maximum kinetic energy of the given electron. So what actually happens in the reverse process, that if we see the photons are coming, okay, the photons are coming, photons is striking the given electron, okay, the photons is striking given electron, it carries a momentum. So what actually happens during the collision, momentum transfer happens, and this electrons will get momentum and this will come out of the surface. So when this will get momentum, this will be moving with certain kinetic energy also, depends on the incident energy. If it exactly matches with the threshold frequency, then no energy, kinetic energy will be 0. So this particular term we can write, we can elaborate this energy of the light or energy of the photon here. In this case, here we can write this one is energy of the photon. So this will be energy of the photon we have, and what is energy of the photon we can have? That is h mu is equals to, in terms of this, h mu naught plus Kmax. Okay. Next we have, that is hc by lambda. In terms of the lambda, we will be writing this hc by lambda plus Kmax. Depending on the different situation, we'll be using different formulas depending on the requirement of the different cases over here. So this is what Einstein photoelectric equations. The only condition is that whatever the mu should be greater than mu naught for this formula to work. Otherwise, photoelectric effect is not possible. So let's discuss one more term, that is the stopping potential. Here we have what is stopping potential. In the same setup we have here, this side we have cathode, this side we have anode. So what we are doing in the first case, you can check this side where polarity is negative and this one is positive. We are doing the opposite. We are making the anode negative now, okay, and this cathode as positive. And this setup will be like this only, that light is incident on this, okay. So light incident on this, light incident on it. So what actually happens when the light is coming out from this, okay, electron is getting ejected. And when the light mu is greater than sufficient mu naught, electrons will get the kinetic energy also, okay. But suppose if you want to stop this photoelectric effect, for that what we are doing, we are giving the negative potential to this electrode, that is the anode, and this will become negative charge. This itself will get accumulation of this negative electrons over here, and this electron is coming, and we have to stop the maximum kinetic energy while electron. If you are able to stop the maximum kinetic energy while electron, then this problem is solved, that we are able to stop that photoelectric effect. So to stop the maximum kinetic energy of electron, we should be knowing maximum kinetic energy should be equal to E multiplied by V naught. And what is V naught here? V naught is what we define stopping potential, and this potential will be negative, and mostly in calculation magnitude will be taken, V naught will be taken as positive, depending on the options will be taken. So here at this minus V naught will be taking this. What actually happens, this particular term, that is retarding potential, also we call it as stopping potential. It is stopping potential, this fastest electron will also get stopped, so that photoelectric effect is not happening further. So this potential at which the electron will get stopped, we call it a stopping potential, and that is given by this particular relation, that is Kmax equals to EV naught. Now, so we'll be checking the graph for this. So threshold frequency, threshold wavelength, and certain things that we have to discuss, we already discussed. Let's discuss how it depends on the graphs, okay. Stopping potential also we discuss, minimum potential or minimum negative potential required to stop the fastest moving electron. And if we see the graph of this, that is graph is plotted between this photocurrent versus